Swayamprabha. Digital India. Educated India.
It is my pleasure to extend greetings again to all of you. We are now on to the module 4 of this week. In this week we will actually explain with the help of a working code how to write a code, and for that purpose we have taken a test case problem of flow in a lid driven cavity. In the last 3 lectures we explained about grid and then different components of u momentum equation, v momentum equation. In other words, how to write separately for convection term, diffusion term, and put them together to get u star, v star. And then we also explain how to enforce boundary condition. As soon as you solve momentum equation, we have to impose boundary condition, and for the left wall, right wall, bottom wall and top wall respectively. Now, in this module we are going to talk particularly about the pressure or the projection method, how to solve pressure Poisson equation and enforcing boundary condition for pressure Poisson equation and corresponding code with explanation. So, for the sake of continuity, I am listing here all the steps that we mention to solve this particular problem. So, grid generation we have already done, discretization of the governing equation, separately convection term, diffusion term, solving the momentum equation to obtain intermediate velocities u star and v star. Now, in this class we are going to talk about how to solve pressure Poisson equation. Then we project the intermediate velocity onto the divergence free space using the pressure calculated through the previous step, correct the velocities, and then we repeat the steps until the solution is converged. The last step, once we get all the variables, we look into the flow through different post processing. We mentioned we are following to do the pressure velocity coupling a procedure called projection method. In projection method there are 3 steps involved. First, solve the momentum equation without considering the pressure term. So, we obtain what is known as a intermediate velocity denoted as u star and v star. Because we have not considered pressure term, it will not satisfy the continuity equation. In other words, del dot v is not equal to 0. Then you solve the pressure Poisson equation to obtain pressure gradient, enforcing continuity or divergence free condition, that is del dot v equal to 0. Project the intermediate velocity onto the divergence free vector space using the pressure calculated in the previous step, and in incompressible flows the pressure acts as a Lagrange multiplier and ensures continuity is satisfied. This is a step that involved in pressure velocity coupling. Please recall we listed 4 methods: Mach algorithm, marker and cell algorithm, simple and different versions of simple, that is simple or simple C, and then projection method. For this demonstration we are using projection method. This is a third step, that is using the intermediate velocity obtained in the previous step, that is by solving u momentum and v momentum equation. Pressure Poisson equation is set up and it is solved. So, we have del dot u star by delta t equal to del squared p, which is the pressure Poisson equation. Discretization of the pressure Poisson equation is done using the standard 5 point stencils, such as dou squared p by dou x squared plus dou squared p by dou y squared minus sign is equal to minus 1 upon delta T multiplying dou u star by dou x plus dou v star by dou y. This is the pressure Poisson equation. This is separately obtained. We already listed how to obtain this pressure Poisson equation. So, you consider the left hand side of the pressure Poisson equation, that is minus dou squared p by dou x squared plus dou squared p by dou y squared. Because it is second derivative, we use second order central differential scheme for pressure. So, we get p at I plus 1 comma j plus p I minus 1 comma j minus 2 p I comma j by delta x squared for the first term. Now, for the second term, that is the second derivative in the y direction, we have p I comma j plus 1 plus p I comma j minus 1 minus 2 p I comma j by delta y squared. Pressure is not indicated at any time level. To account for the fact that pressure acts as a Lagrange multiplier imposing the continuity constraint. That means, the pressure is only local at that particular time. The above discretization results in what is known as a pentadiagonal matrix. Again, please recall we mentioned different matrices possible: tridiagonal matrix, just diagonal, and pentadiagonal matrix of different form. So, this pressure Poisson equation, discretization of the pressure Poisson equation will result in pentadiagonal matrix. Coefficient matrix is formed with a special importance to the corner as well as edge nodes. So, we have again ghost grid and ghost cell strategy to impose the boundary condition. Please recall what we learned in the two previous modules. Separately we have done for u velocity and separately we have done for v velocity when we respectively solve u momentum equation and v momentum equation. Because we are following staggered grid arrangement of variable storage, we need to have one extra grid on either side for the respective equation, and pressure is at the center of the cell in the staggered grid arrangement. So, we have ghost grid as well as ghost cell on all the sides, that is both x as well as in y, and those are shown by this red color line. So, these are all extra cell in x direction, similarly in other x direction, and for y direction at the top as well as at the bottom. So, P staggered grid with the ghost cell for boundary condition implementation. Because of this extra ghost node or ghost cell, number of p velocity unknowns now becomes I max plus 1 into j max plus 1. Consider the left hand side of the pressure Poisson equation. So, again that is what I am showing here. We already mentioned we are following second order central differential scheme to get the second derivative, and then we mentioned it will result in what is known as a pentadiagonal matrix. So, corresponding code is displayed here. So, T and P is number of nodes I max minus 1 into j max minus 1, that is the total number of pressure nodes, and for j 2 to j max and for I 2 to I max, if j is not equal to j max, then we have defined this. So, this is for coefficients of pressure for the node I comma j minus 1. We have written similar thing for each location. So, this for example, this particular line is for coefficients of pressure at I comma j plus 1. We have written similarly for each. So, coefficient for P at general nodes I comma j is shown here. I would like to emphasize once again these special treatments, that is I j minus 1, I j plus 1, I minus 1 j and I plus 1 j, these are for corner nodes and edge nodes, and this particular line is for all internal nodes. So, the nature of pentadiagonal matrix after the coefficients are evaluated is shown here. So, we have D1 A1, then there is a element 0, then there is a value F1. Along the diagonal of the coefficient matrix we have value, immediately below subdiagonal we have value, immediately above subdiagonal we have value, then we have zeros and then values F1 to F5, F6. Similarly, on the lower side E4 to E9 after the 0 values, and pressure column vector, unknown column vector is multiplying that coefficient matrix equal to central differential scheme known value is written as a known vector on the right side. If you observe the nature of the matrix, we conclude that the first and second subdiagonals have some terms, that is what is this, which are zeros, and we have to carefully construct the coefficient matrix taking that into account. We have explained how to do the LHS of the pressure Poisson equation. Now, we do for right hand side of the pressure Poisson equation. The right hand side of the pressure Poisson equation has actually the source term, which is related to the intermediate velocities u star and v star as shown here, that is minus 1 upon delta t equal to dou u star by dou x plus dou v star by dou y. We write the finite difference form of the source term as shown here. So, 1 upon delta t u star evaluated at I comma j node minus u star from I minus 1 comma j node by delta x plus v star from I comma j node minus v star from I comma j minus 1 node by delta y. So, corresponding code is displayed here. So, the right side is actually right side column vector is actually given as BP. Comments are written first few lines. So, RHS vector of the pressure Poisson equation. This function calculates the RHS vector of pressure Poisson equation by considering divergence of the intermediate velocities u star and v star. So, we define the function with the corresponding arguments as shown here. Initially they are set to zeros with the memory size related to number of nodes as shown here. Now, for I 2 to I max and for j 2 to j max BP is calculated as shown here. This is exactly what we explained in the previous slide, only thing it is written in MATLAB code form as shown here. So, we have calculated separately the right side term and separately left side term. Now, we have to enforce the boundary condition for pressure. For the present case, that is for the pressure, we enforce boundary condition in the form of a Neumann type. For velocity, we enforce through Dirichlet boundary condition. So, the left side wall dou p by dou x equal to 0, and using the ghost nodes we have to have extra ghost nodes to enforce the boundary condition. So, p at I is equal to 2 and for j 2 to j max minus p at I is equal to 1, again j 2 to j max by delta x equal to 0. So, this is actually dou p by dou x equal to 0. So, if you rewrite this equation, so we have p at 1 comma 2 to j max equal to p at 2 comma 2 to j max. Similarly, for the right side wall, again Neumann type boundary condition for pressure dou p by dou x equal to 0. We have I as I max plus 1, 2 to j max for j inside of that wall. So, p I max and j 2 to j max by delta x equal to 0. So, if you rearrange, we get value for the ghost cell node such as p I max plus 1, j going from 2 to j max equal to p I max, that is inside the right side wall, and for j it is 2 to j max. Similarly, the top wall dou p by dou y equal to 0, again similar arrangement, only thing you have to now pay attention to J value. So, it is J max plus 1 which is above the top wall, and J max which is just below the top wall equal to delta y. So, that will result in dou p by dou y equal to 0, and if you rewrite p 2 to I max for x direction and J max plus 1 is just above the lid equal to p 2 to I max for I, and J max it is just below the lid. Bottom wall dou p by dou y equal to 0, again using the ghost nodes. Now, we have to pay attention carefully again for value of j. So, I is from 2 to I max, j is 2 minus again p at 2 to I max, and j is at 1 by delta y is equal to 0, and you rearrange we get expression as shown here. So, they are all implemented as shown in this code. We will come to this comment after explaining this. So, all Neumann type boundary condition for pressure boundary conditions P at 2 to I max comma 1 equal to P 2 to I max comma 2 on the left side. Similarly, for the right side wall, bottom wall, top wall, as we explained in the previous slide. Only thing, it is written in MATLAB code language. Now, there is a procedure called pinning the pressure at a particular point. So, when you are using Neumann boundary type of boundary condition for pressure, it renders the coefficient matrix singular. So, if when you get a matrix as a singular, it is very difficult to solve. So, to avoid that situation and to make the matrix invertible, pressure has to be pinned at a point. That is, we are actually interested in a problem only the pressure difference, not the actual pressure itself. We use this. So, we say at any one point pressure is made to 0 and all other pressures are referred with respect to that point, and this process is called pinning the pressure. So, for the matrix to be invertible, the pressure has to be pinned at a point. Pinning the pressure at a point does not affect the overall solution, because the absolute pressure does not matter. What matters is only the pressure gradient. So, if you look at u momentum equation, v momentum equation, we have only dou p by dou x and dou p by dou y. So, all that it matters is the pressure gradient. Actual pressure itself is not that much important, and this is used to set a procedure called pinning, and that helps to make the coefficient matrix as invertible. So, pin the pressure at a corner. So, we can pin pressure at any point. In this example, we have pinned the pressure at one corner, that is what is F at 1 equal to 0.0. Now, solve the pressure Poisson equation as shown here. Okay. We can again set convergence criteria separately for pressure Poisson equation and then return and end. So, in this module we have learned in detail how to solve a pressure Poisson equation from the predicted velocity u star and v star. The pressure Poisson equation has a left side as well as right side term. We looked at left side term and right side term separately. We also learned a procedure called pinning the pressure, and pinning the pressure helps to make the matrix invertible. Then we also learn how to enforce boundary condition for pressure. For the pressure, we follow Neumann type of boundary condition, and to enforce the boundary condition, and we are because we are following staggered grid arrangement, we need to have a ghost node on all the sides for pressure. This is appropriately accounted, and we looked at corresponding lines in the code. In the next module, we are going to see complete assembly of the code and solution uptime, how to do post processing from the solution, corresponding display of the code. Thank you.